Hello everyone. Welcome to ComSci Connection. This is going to be a recursive demonstration of a maze puzzle. How exactly we solve a maze. First of all, I'm going to make sure that I give credit to the author of this code. This is Steve Kautz's code originally, and for that purpose, or because of that reason, I'm not going to show this code. It's a past assignment in 227. It's very possible it could be a future assignment again. I don't want to cause any sort of I don't want to give away any of Steve's secrets up his sleeve and things like that. I don't want to give away too much that might prevent him from ever using this again, because this is a classic problem in computer science, and it's a very good project, a very good illustration of exactly one of the best uses for recursion. So what you are going to be able to see here is you're going to be able to see the stack trace here. I guess I won't be able to get rid of all of it, but that's alright. You'll be able to see the stack trace, you'll be able to see exactly what's going on, and you're also going to be able to see a little maze over here. I will go through more than one example here so we can get a couple of different ideas of how this is going to work. But what you need to understand right now is that we called this maze search from the original point in main, and we basically said that we gave it a start point, which was this point right here, this blue point, which is 6, 1. The natural step, I mean, that cell was already signaled as the starting point, so no changes have been made right now. I've got this sitting up and waiting. So as we know from the Blackboard example that Andrew that did for all of us here at ComSci Connection, we know that the first step here in every single cell is to determine our base case, just like any recursive problem. And our base case in this scenario would be, have we reached our goal? Well, obviously we, as intelligent human beings, can tell immediately, well, of course our start is not the goal, but the computer needs to check that, and then after that it's going to say, well, if I'm not the goal, then I must be part of, there must be some sort of change that I can make, or some sort of further step that I can continue on. So since we know there's going to be a solution to this maze eventually, we know that eventually we will reach it. The computer doesn't really know anything more than the steps that you give it, and in this case we tell it, okay, go ahead and find your neighboring cells. Then one at a time we're going to go through each one of the neighboring cells and recursively call this search method on it and force that change to occur on that cell until eventually we'll find our goal, we'll reach our base case, and then we'll terminate. One last thing I will say about this algorithm is that it does construct the path. Obviously, if we want to find the path, that's great, but we want to actually be able to use it. We want to tangibly recover something from this algorithm. We want it to serve some purpose, and we want it to tell us how to get to the goal. You know, it's great if it can solve it, but what good does that do us in the end? So we are going to see this get constructed in the end, and we'll see a little fancy printout of the exact path that's going to happen. But let's go ahead and jump right into it. We're in our very first call to search, and it's given this initial cell, the starting cell here, the blue one, and it basically says, hey, go ahead and search that cell. So we're going to, obviously it's not the base case, so it's going to continue on by finding all of its neighbors, and we obviously know that there's only one possible neighbor here. So I'll go ahead and step over this. Actually, I want to do resume, yeah. So it's going to call another search. And at this point, we know that it's gone up one cell. Now, you can't really see that, it hasn't illustrated yet, because at this point, we haven't made any change to this new cell. All we've done is we've told it to go ahead and search that cell. We know that it's not the goal, so the base case scenario won't reach, and then it's going to basically mark this cell as currently examining. It's going to mark it, and you're going to see it show up. It's going to change colors here, and it's going to immediately start searching all of its neighbors. So let's resume over that. We see it's been marked as yellow to say that it's currently being searched. Another call to search has been made on our stack. We can see that it's now searching for 1, which is 0, 1, 2, 3, 4, 1. So we're in this cell right now, so we've gone up. Now, could our algorithm have chosen to go right? Yeah, absolutely. The only reason why it went up is because the way this code was originally written. It just said, hey, we're gonna, whoever, well, Steve, when he wrote it, he made the list of neighboring cells, for some reason, return up. You could write your algorithm to return right first or left first, or have some kind of priority system in place. It really doesn't matter. One way or the other, it's still going to find the solution the same way. But that's just the way this one works. It doesn't have to be that way. Just to explain that. But at this point, we know we've gone up, so the same thing's going to happen here. It's going to find all of its neighboring cells. In this case, there are two. There's one up, and there's also one down. Well, the thing is, if the cell is already being marked as searched or as unsuccessful, in other words, it was part of a path that wasn't any good, didn't reach us to the goal, and it has been marked that way, then it's going to skip it. So we know that it's going to go up in this case. So I'm going to go ahead and press resume again. We're going to see a fourth call to search has been made because it recursively called on the cell one above it. So now we're at 3-1. And we've marked our previous cell as currently being searched, or part of our current path. Now again, we're going to resume again. We're going to see that we've gone up again. We're now at 2-1, and we are now in this cell here, and we've marked our previous cell as being searched, and we have our fifth recursive call on the stack. This is going to keep going just like this. We're at 1-1. We've got another call on the stack. We've marked another cell as currently being searched. We'll go ahead and step over again. We're now at 1-2, so we're right here, which we can see is a dead end. We know that right away. We've got another call on the stack right now where this currently exists, but what's going to happen is it's going to ask for its neighboring cells, and it's going to get one that's already being searched. Now at the point when you run out of neighboring cells that can be searched, you know that it's a dead end. You know that it is no good. So we're going to go ahead and mark this cell as failed, and we're going to return that status. We're basically going to tell wherever this call to search was originally made that this cell is no good. That return statement will mark that direction, or that it will know that, okay, the previous call where we were at 1-1 right here, this call here, knows that it only has two neighboring cells, one to the south and one to the right, I should say east. So if it called to the east and that returns failed, and it can't go south because south is already being searched right now, then it knows that it has run out of neighbors as well, and it will also return failed. So we're going to see that as I hit resume here, it's going to automatically mark 3 cells as failed, because the reason why it didn't stop one at a time there was because my breakpoint was telling this computer program to stop every time it was starting to search a new cell. And since 3 levels here all terminated, and we can see that we've lost we've lost 3 of them off of the stack. They basically returned failed, the cells were marked as red, and now we're back to another cell that still has neighbors to continue searching. So we'll go ahead and resume. Another item has been added onto the stack. We've marked this cell as being searched. We're now at 3-3, which is this cell right here, this gray one. Obviously it's a dead end, so as I hit resume, you're going to see several more cells being marked as failed. Now we're back to this cell, 5-2. You've noticed that several of the recursive calls have fallen off of the stack. We can see that we were not able to find a path through those cells, so they automatically returned failed because they didn't have any more neighboring cells to search. This one does though, so we're going to go to the right. We can see we're at 5-3. We're going to go to the right again, 5-4. We're going to go to the right again, 5-5. Now we're going to go up, 4-5. Going to go up to 3-5, going to go up to 2-5. You can see how many calls to search we have building up here on our call stack, but all of the previous ones are just sitting there waiting because they haven't gotten an answer yet as to the status of the direction we're going. And obviously we know that we go one more, it's going to be 1-5, and now we're currently in this gray cell. We haven't marked it yet. We haven't marked it anything yet, but we know that it's not the goal, so our base case isn't the case. So it'll get its neighboring cells, and it's going to go one to the left. And then in this case, it's going to say, yep, 1-4, that is the cell right here, and that is our goal cell. So when I hit return here, you're going to see that it's immediately going to fall back, returning success to each previous cell, and then adding that cell's coordinates to a list of successful coordinates, eventually giving us a nice little output here at the very bottom of the screen. So I'm going to hit resume here. We're going to see these recursive elements fall off the stack. We have terminated our program. You can see that it's completed, and we are given this nice little printout here along with a fancy little green path to see. So that was a quick example. Let me jump over into a more intense example. Let's get that going. And let me resize my window here a little bit. Actually, one thing I think I will do... No, this will be alright. So, I'm not going to go through with nearly as much detail as I did on the previous one. Obviously that would take a long time, but I am just going to click through this, and I want you to pay attention to the call stack over here on the left as we step through this, and you'll see how things will build up and then they'll fall back down when it returns fails. So there we go. Notice that this call stack gets quite large when we're building a path so long. Let's step through it a little faster. Now this could cause a problem if we end up running out of memory, but I know that this won't happen. So notice how it was able to mark many cells as red there. And look at how many calls on the stack we have. All these recursive calls. It's going to mark several of them as failed. And we're down to just them again. We're going to continue searching. Now notice here that we're currently in this cell right here at 213, and it's going to notice that its only neighboring cells are already being searched, so that at the same sense as running into a dead end, knows that it can't go that direction, or that direction was no good. You basically have just gone in a circle. Same thing is going to happen here. We're going to step through this, suddenly find a dead end, and then see how many calls we now have on our stack. So our stack kind of cleans itself up over time. So we're going to continue stepping through, stepping through, stepping through, stepping through. We're about to hit a dead end, but it only marked one cell as red because this cell, the previous cell, still has neighbors to search. We keep going, keep going, keep going, and I'm going to go ahead and take this breakpoint off. And I think we'll just go ahead and run it. You get the idea by this point. But you can see how systematically it's going to go through and check every single cell. It's going to find where it fails and continue in the current path. And eventually, see, these paths, these cells we started out with at the very beginning are still in the yellow. They're still on the current recursive stack, and therefore their recursive calls still show up on the list of the stack trace, as we call it. They still show up there. And so when we end up finding the path and we go back to build our path from scratch, we're eventually going to use those cells in our path. So, and we have found the goal. So each cell is being marked as green as its coordinates are being added to our path. And when it finally returns, we'll get a nice output to the screen. And just for the record, this is slowed down quite a bit. There's a delay. If I take the delay off, I believe I actually did test this last year at some point. It will solve this particular maze in about 16 milliseconds or something like that. I'm not 100% sure, but it's very fast. Like, you'll click run, and before this Java box even pops up, it's done. It's completely filled all of this trail in this green path. But hopefully that was pretty cool just to watch that happen, and hopefully this video helps you understand a little bit more about recursive calls and about the stack and about how this all helps you. And I hope that you can get familiar with tracing through these things on your own in debug mode. That's one of the real advantages of doing these kind of demonstrations, is that you can actually see how these steps take place and how it appears to the computer, how it shows up on the call stack. And if you want to try to gain an understanding, a deeper understanding of these types of things, if you do it on your own computer, on your own time, even with a simple example, you will be able to see every single step, and you can make it run as slow or as fast as you want, so you can make sure you understand it bit by bit. So great, hope this helps. Let us know if you have any questions. Otherwise, good luck.